Generic types are types that are parameterized by other types. We've already seen 3 examples of generic types. These are option, result, and vectors. Let's see how these are generic types. How are they actually defined? For an option, this will be a enum. The name of the enum is an option. This option is a generic type, so it is parameterized by another type. We declare that this enum is a generic type like this. Here the capital T is a type placeholder. So inside here you will have your concrete type when we create this enum. For example, an option of U32 will have a U32 over here. An option of Boolean will have a Boolean over here, and so on. This is a type placeholder. We'll call this T. An option can take on 2 possible values, some with a value of the type T inside, or none. So this is how an option is defined. It is a generic type with the type placeholder T. Let's look at an example of how this would turn into a concrete type. For example, if you had again U32, then this T will be replaced by U32, and sum will contain U32. This will mean that if the value exists, it will return sum with the value of the type U32 inside. Otherwise, it will return a none. Another example, let's say we have a string. Then this will mean that if there's a value, then it will be sum with a string inside. Otherwise, it will be a none. Of course, this logic works for many data types, so we replace it with a type placeholder. This is an example of a generic data type. Now let's look at an example of a generic data type for result. What does it look like? How is it defined? Result is also a enum, result. Inside here, we put in our type placeholders. Recall that a result takes on 2 other types. The type that is returned on a successful case and the type that is returned on the error case. Now notice that here we define 2 type placeholders, T and E. How are they used? In the OK case, we return a type of T wrapped in OK. In the error case, we return the enum value of error with the type E inside. So this is how an option and a result is defined. I'm going to comment this out so that the code still compiles, since both of these enums are already defined inside Rust. How about a vector? Well, inside the main function, when we create a vector, let's say that b of the type vec, and then inside here, we'll put our concrete type. And this will be equal to vec, and then inside here, we'll put in our values for each element of the vector. For example, if we put in U32, for example, 1 U32 and 2 and 3, the vector elements are of the type U32. So this type placeholder T will be a U32. If we change this to a I32, then this U32 over here will be a I32. You might be asking, why are generics useful? Generic types are useful when you want to reuse some kind of data structure or logic, but that logic or the data structure doesn't really depend on the type that it stores. This is the case for an option, result, and also for vectors. The data that it stores doesn't really matter. For a vector, we want to store elements of the same type and also be able to add and remove elements from a vector. The type that it holds doesn't really matter. It should work for booleans, U32, I32, strings, and so on. So this is where generic types are useful. Now let's look at 2 more examples. How to define our own generic type, and how do we use generic types inside a function. Let's start by defining a generic data type. So let's say that we have a struct called point. Inside this point, we'll store 2 values. The coordinate x we'll store as I32, and the coordinate y we'll also store as I32. This represents a point in 2D space. To initialize this, let's say that p is equal to, the type will be point, and this is equal to, let's say, point, x0, and y0. Now, we could have also created a point where this type is a U32, and we could have also created a point where both of these types are floats. So maybe we wanted to create a point with U32, and maybe we wanted to create a point with F32. Currently, we can only create a point of the type I32. So how can we turn this data structure into a generic data type? Looking from the examples above, we sort of have an idea of how to declare generic types. For the struct, we would declare the type placeholder, T, and then let's replace X with the type T and Y with the type T. Now, going to the main function, we also need to update this. Looking at the syntax for vector, we need to put in a type placeholder here. Here, we'll need to put in our concrete type. If you wanted to create a point where the x and the y are I32, here we'll put an I32. If you wanted to create a point with U32, you will replace this I32 with a U32. And finally, if you wanted to create a point of the type float F32, then we will replace the U32 with F32. And also, we'll need to update the data that is stored. We'll need to say 0.0 to make sure that this is a float. So this is an example of how to create a generic data type. Now let's look at a simple example of a function that operates on generic types. So let's begin by having a function that takes in, let's say, a of the type u32 and b of the type u32. And this function will swap the values for a and b. The return type will be u32 and u32. All we do here is simply switch a and b. So if you pass a and b, then this function is going to give you back b and a. Let's call this function swap inside the main function. So let's say that mut a is equal to 1 and that mut b is equal to 2. We'll call the function swap on a and b. The value that is returned will be b and a. So let's reassign this to a and b. What this code is doing here is it's replacing the value for a and b. After calling this function swap, a will hold the value for b, which is 2, and b will hold the value for a, which is 1. This function swap can also work with other data types. So now let's turn this into a generic type. The first thing that we'll do is put our type placeholder. Let's say that we have a type called a, and then replace all this u32 with the type a. Notice that inside the main function, we didn't have to make any changes. All we had to do was declare a type placeholder. So now we've created a function that works with generic types. We'll make one more improvement. The type b doesn't have to be equal to type a. We can have two different types. So let's declare a new generic type. Let's call this type b, and then replace b with b. How about the return type? Well, the return type is going to be b and then a. So now the swap function takes in two inputs, a of the type capital A and b of the type capital B. It simply swaps the order and returns b and then a. The return type is capital B and then capital A. We now need to update our main function. Let's say that type A is of the type u32 and type B is i32. We pass in u32 and then i32, and then to A, we're reassigning the type i32. And then to the variable B, we're reassigning the type u32. So this code will not compile. Try to execute the code, and you can see that the code does not compile, since we're trying to reassign values of the different type. So let's update the code and fix the compilation error. The solution here is simple. All you have to do is remove the mut keyword and then reassign the variables. So A here will be of the type u32, B here will be of the type i32. But on the next line, we're redeclaring the variables. So now A will be of the type i32 and B will be of the type u32. Let's execute the code again, and this time the code compiles. So in this video, I showed you some examples of generic data types, how to declare it, and how to write functions using generic types. Imagine that we have a struct called point, which represent a point in 2D space. It will store two fields, the x-coordinate and the y-coordinate, as f32. In this video, I'll show you how to declare methods and static methods on a struct. The syntax that I'll show you works both for structs and for enums, but in this video, we'll be using a struct. First of all, what is a method? A method is simply a function that is attached to the data type. In this example, we're using the data type point. We're going to be attaching a function to this struct point. By declaring methods, what would this allow us to do? Well, inside the main function, let's first create a point. Let's say that p is equal to point with x equal to 0.0 and y equal to 0.0. By declaring a method, let's say that we declared a method to move the point. Let's say move to somewhere. Here, it doesn't matter what we put in. By declaring a method, the function will be attached to this instance of a point so that we can use a syntax like p.moveTo to call a function. Now in contrast, if we didn't have a method, then we would need to have a function called moveTo and then pass in the point. In this case, inside the main function, the syntax will look like moveTo and then we pass in the point. So that's the difference. Now, how do we declare a method? We start with the keyword impl, followed by the type that we want to implement the methods for. This is for the point. And then inside here, let's create a method that operates on an instance of a point. So there's going to be two distinctions. There's going to be functions that operate on an instance of a point, and there's going to be functions that operate on the type. The functions that operate on the type are called static methods, also known as associated functions. The functions that operate on an instance of the type are called methods. Let's first create a method, a function that operates on an instance of a point. Let's create a function, let's say moveTo. This function will update the x and y coordinates of the struct point. So it's going to take a mutable reference to the point. Since it operates on the instance of this struct point, we refer to this as self with a small s. And then let's put in the two new coordinates, x of the type f32 and y of the type f32. We'll update the x coordinate by saying self.x is equal to the new x value, and then we'll do the same for the y value. So this is an example of a method, since it operates on the instance of the type. How about a static method, also called associated function? The static method will operate on the type. A good example is a static method that will instantiate the type. For our example, let's say we have a function called new. This function is going to create a new instance of the struct point. For the inputs, we'll pass in the x coordinate f32 and then y coordinate f32, and then we'll return this type point. Here we can declare this as a point or as self with a capital S. Self with a capital S refers to the type. In this case, this will be point. And then inside here, again, we can say point and then pass in the x and the y inputs, or we can also say self. They both do the same thing. Okay, so this is an example of a static method. Let's now call these two methods inside the main function. Here we have a point, so we can call the method moveTo to update the x and the y coordinate. To do that, we first need to redeclare this variable as a mutable variable. And then we'll call p.moveTo, and then let's pass in for x, let's say 1.0, for y, let's say 2.0. Let's try to print this point out. To do that, make sure that the derived debug attribute is attached to the struct point. And now let's print this out. Execute the code, and we get the point printed out. X coordinate 1.0, y coordinate 2.0. Now let's look at an example of a static method. This function will create a new point with the x coordinate and the y coordinate. We can actually modify this example. Instead of directly creating a point, we can call point, : the function new that we defined, and then for the x coordinate, that's passed in 0.0, and for the y coordinate, we'll also pass in 0.0. The code over here and the code above does the same thing. So this is an example of a static method, and this is an example of a method. To declare methods or static methods, you prefix the type with the keyword impl, and then inside the curly braces, you define the functions.
It's 8 o'clock.
Imagine a situation where we have a function and we want to pass in various types for the input. For example, let's say that we have a struct called Solidity and Viper, two programming languages. And then we have a function called compile. What we want from this function is that it would take in a language and then output a command that will compile the programming language. We want this function to be able to take in both Solidity and Viper. In Rust, we can accomplish this by declaring that the input is some type that implements a trait. Instead of declaring the input as a concrete type, we'll declare it as a trait. This tells Rust that the input that is passed in is some type that implements a trait that we define. There's two parts to a trait, defining a trait and then implementing a trait for a type. In this example, we want the types that we're going to pass in here as language to have a single function called compile, which will output the command to compile the language. To define a trait, we start with the keyword trait. Let's name this trait compiler. All types that implement the compiler trait will have a command to compile the language. Let's call this function compile. It will take in two inputs, the self, this will be the type that implements this compiler trait, and let's also pass in another input. Let's say that the file path to compile, file path of the type string slice. Here we're passing in a string slice since the file path can be read-only. And then it's going to output a string that represents the command to compile the contract at this file path. So now that we defined a trait, let's now implement the trait for the struct Solidity and Viper. To implement the trait, we'll start with the keyword impl, followed by the trait that we want to implement, impl compiler, and then followed by the type that's going to implement this compiler trait. Let's start with Solidity. We need to implement the compile function. For simplicity, we won't worry about whether the command is a correct command or not. This is just a simple example. Let's say format. To compile a Solidity contract, we'll need to call a command called soak, Solidity compiler. And let's say we also want to pass in the file path. By the way, this format macro is used for string interpolation. Here it's saying inside these curly braces, put in the input, which will be file path. This will produce a string with soak followed by file path. Now that we implemented the function compile for Solidity, let's also do the same for Viper. I'll copy this code and then paste it here. Compiler for Viper. Let's say that the command to compile Viper contract is Viper. Now, I'm not sure if this is the right command, but for this example, it will do. We're not so worried about the actual command to compile the contract. We're focusing on how to declare traits and how to implement traits. Okay, so now we have the struct Solidity and Viper that implement the compiler trait. Now let's move on to the function compile. Both the Solidity and the Viper struct implement the compiler trait. So now we can specify here for the input, say that the input lang will be a type that implements the compiler trait. To do this, we'll type impl and then followed by compiler. Now remember in Rust that all data sizes must be known at compile time. Here it's saying some type that implements the compiler trait. This type currently is an unknown size. To make it a known size, we put it behind a reference. Now this code will compile. Since whatever type that implements the compiler trait is behind a reference and the size of a reference is known at compile time. Inside the function body, we'll call the function lang.compile. The function compile takes two inputs. Self will refer to the instance of the type that implements the compiler trait. In this code, this will be an instance of Viper. The other input is the file path. Let's pass the file path from the input to the function compile. Say file path of the type string slice, and then pass it into here, file path. Now let's see some examples of how to call this function compile, and also how to directly call the function compile on the trait that implements the compiler trait. The first step is to initialize these two structs, Solidity and Viper. So let's start with Solidity. Let's say that sol is equal to Solidity. It takes in a single input to initialize this struct version. This will be a string, let's say 0.8.toString. Next, we'll create the Viper struct. Let's say that by equals Viper and then version. Let's say 0.4.toString. The first way to call the function compile is to simply call sol.compile or viper.compile. Let's print this out. For the file path, let's say hello.sol and hello.vy. Execute the code, and it says Solidity compile, soak hello.sol, Viper hello.vy. So that's the first way to call the function compile on Solidity and Viper. The other way to call the function compile is to simply pass it into the function compile. So we can say, let's copy these and then paste it here. So we'll call the function compile, passing in a reference to the Solidity struct. Here, it is reference to something that implements the compiler trait, and the Solidity struct implements the compiler trait. And for Viper, we'll do the same. Something that implements the compiler trait. This will be a reference to Viper. Let's execute the code again, and again we get the same outputs printed. So these are two ways to call the function compile on a type that implements the compiler trait. We can directly call it, or we can pass it into a function where the function takes in a trait as input. So now notice what we have done. The function compile takes any input that implements the compiler trait. In our example, we are able to both pass the solidity and the Viper struct into this function. For the final part of this video, I'll show you that we can have a default implementation for the trait definition. Inside the compiler trait, we define a function called compile. All traits that implement the compiler trait must implement the function called compile. Let's also create another function. Let's call this help. This function, when it is called, will return some documentation on how to use the compiler. Inside the trait definition, we can also define a function. In this case, this will be the default implementation. For example, let's say that when the function help is called and the function help is not defined inside the implementation, in our example, we'll leave a blank implementation for the function help on Solidity and Viper. In this case, the code inside here will be executed. So let's say that when the function help is called, we'll return unhelpful documentation, let's say good luck. Now notice that both for Solidity and Viper, we don't implement this function called help. This will be the default implementation. And now, going to the main function, we'll be able to call the function help. Let's print these out. Let's copy these and then modify it. Call the function help on the Solidity struct, and then call the function help on the Viper struct. Execute the code, and we get Sol help, good luck, Viper help, good luck. So in this video, we looked at an example of how to define and implement a trait so that we can pass multiple types as a function input.